This is a problem from the Wade textbook in Chapter 6 on carbocation stability, which has some pretty useful principles. So first of all, the question was to rank them from most stable to least stable. And so what I have here is the rankings. So the most stable one is the tertiary cation that is allylic. And then the second one would be the allylic cation that is in resonance from a primary position to a secondary. So if you look at that and say it's a primary carbocation, it's not, right? It's allylic, and that makes a big difference. The third most stable then would be the tertiary carbocation itself, followed by a secondary, and then of course least is that lone primary. So there's a big difference between these two right there. So beyond that though, we should take note that there are resonance structures for the ones in resonance, obviously, for the allylic ones. So what we can do is show that these electrons can move up here, okay? So they're going from the pi bond and they're going to make another pi bond, and so I start where the electrons are in the double bond and end it between the two carbons. And so we'll end up with this resonance form. And what I should say is, because I moved electrons away from this carbon, then I need to have a plus charge located there. So, and that's still the methyl group. So that would be the two resonance forms for that one. I can also do this here. Again, I'm going to move those electrons only to where there's room for them. So since there's an empty p orbital where the carbocation is, then I can move electrons into that. So then I will have a new form that looks like this, with the carbon that had the double bond on it out here now has the plus charge on it. So a couple of resonance forms. But wait, there's more concepts that we can use here, because something to learn about carbocations is that they're they're rearrangeable. So in this position I have an H, and so I should consider that I can actually move that H. That can migrate out here to this carbon. So that would be called a hydride shift. And notice that I'm switching to a reaction arrow because something's actually moving. So in the case of these two, these are not equilibrium, but resonance arrows. So double-headed arrows, resonance arrows, because I did not move any atoms, only electrons. In this case though, I've got a reaction arrow because something is actually changing. So I've moved the position of that hydrogen out to the methyl group, and then that leaves the carbocation in this position. And now I have a couple of matching structures actually. This one matches this one. So that was supposed to be a highlighter. So those two now match because of the hydride shift. Now, what other kinds of changes can I have? Well, if I have a secondary hydrogen, so right here I have a hydrogen again. I better switch that back to the right thing. And that one can also shift over to this secondary position, and so that will give me this new structure of a tertiary carbocation. So if I can shift something and get a more stable carbocation, then I will. Those somethings are typically small groups like hydrides preferred. Methyl groups can shift, but also I can change the size of the ring. So if I have this wacky carbocation that's on the primary position, which I said don't do that, but if I were able to kick something out from that position, let's say a leaving group, I'm going to make that an iodine, okay? I could actually have this kind of thing occur, where this carbon-carbon bond will shift its electrons to kick out a leaving group. Another way to think about it is directly from the primary carbocation, but I'm going to show this is how we would get to that movement rather than drawing a primary carbocation. So if I do that, I should actually not draw that, but instead number my carbons. So I'm going to call this carbon 1, 2, 3, 4, 5, 6, 7. So if I shift electrons from this position up to carbon 1, now I'm going to have a carbon 3 to 1 bond, and I'm going to break the 3 to 2 bond. So 1 to 3 all the way up through 7 means a different size ring. So now I'll have a 7-membered ring. So I'm going to count that as a bond from, there's going to be carbon 2 and 7, 6, 5, 4, 3, and then 3 is now bound to carbon 1. And when it did this shift, it left a hole right there because it moved off from carbon 2, and so that is actually where I'll have a carbocation. So that is a ring expansion, and it allows us to have a more stable secondary carbocation if there was a primary one that might have formed. So we'll go right into this secondary one. So that is how you could get a ring expansion.